June 3, 1944. Amphibious Warfare Training Center, Camp Pendleton, California. Major General Holland Smith stares at the casualty projections for Operation Overlord. The numbers are staggering. Conservative estimates predict 30,000 casualties in the first wave. Worst-case scenarios exceed 50,000. The problem isn't the German beach defenses, though those are formidable. The problem is the 200 yards between the landing craft and the beach. 200 yards of open water where assault troops are completely exposed. No cover, no concealment. Just men wading through chest-deep water while machine guns tear them apart. The briefing room fills with Marine Corps officers, Navy beach landing specialists, and Army amphibious assault planners. They've been studying Tarawa, Anzio, Salerno. Every amphibious landing follows the same brutal pattern. Heavy casualties in the water before troops even reach the beach. We need anti-tank weapons in the water, Colonel James Roosevelt reports. German beach defenses include Czech hedgehogs, Belgian gates, reinforced concrete pillboxes. We can't wait until troops reach the beach to engage them. We need to suppress those positions from the water. You can't fire a bazooka underwater, someone objects. The rocket motor requires oxygen. Water will flood the tube. The electrical ignition system will short-circuit. Bazookas are designed for land combat. Roosevelt nods. That's the problem. We have a weapon that can defeat concrete fortifications, but we can't use it during the approach phase when we need it most. What about naval gunfire? Artillery support from destroyers. Naval guns can't provide precision fire against individual pillboxes while our troops are in the water. The accuracy isn't sufficient. We need direct fire weapons, infantry portable, effective against fortifications, operable in water. How long to develop an amphibious bazooka? Major William Bradford from Ordnance Development pulls out design specifications. Sir, modifying the bazooka for underwater use requires waterproofing the electrical system, redesigning the rocket motor for oxygen-independent propulsion, and creating a sealed tube that can vent underwater. We're looking at 18 months of engineering, probably longer. Smith's jaw tightens. D-Day is in 12 days. The room falls silent. Nobody has a solution. The meeting adjourns. That same afternoon, 40 miles south at the Naval Amphibious Base Coronado, a 29-year-old Navy electrician's mate named Anthony DiMarco is fixing the same problem using lamp cord and electrical tape. Before we continue, if you're fascinated by the battlefield innovations that saved thousands of lives, hit that subscribe button. 72% of you watching aren't subscribed yet, and you're missing stories like this every week. Electrician's mate second class Anthony Joseph DiMarco grew up in Brooklyn. No engineering degree, no weapons design experience, just an electrician's son who spent his teenage years wiring apartment buildings in Depression-era New York. The Navy drafted him in 1942. They looked at his civilian trade and assigned him to electrical maintenance, shore installations, landing craft wiring, communications equipment. Not glamorous work, but essential. DiMarco arrived at Coronado in March 1944 as part of the underwater demolition team support staff. His job was maintaining electrical systems on swimmer delivery vehicles and demolition equipment. But UDT operations brought him into contact with a problem that everyone said was unsolvable. Combat swimmers needed weapons for engaging beach obstacles. Bazookas could destroy concrete and steel, but bazookas couldn't fire underwater. DiMarco watched UDT training exercises in early May. Swimmers would approach simulated beach defenses in chest-deep water. They'd mark obstacles with demolition charges. Then they'd swim back to safety before detonation. The system worked, but it was slow, dangerous, and it assumed the beach defenses were unoccupied. Against a defended beach, UDT swimmers would be slaughtered. What they needed was a weapon that could engage fortifications from the water, immediately, without waiting for demolition timing. On May 15th, Di Marco attended a demonstration of the M1A1 bazooka at the base firing range. The weapon was impressive. A 36-inch rocket that could penetrate 4 inches of armor or destroy a concrete bunker. The demonstration officer explained the firing mechanism. The bazooka used an electrical ignition system. When the gunner pulled the trigger, a magneto generator sent current through 2 wires to an igniter in the rocket motor. The igniter started a solid fuel burn. The rocket launched, simple, reliable, but completely dependent on electrical continuity. Di Marco raised his hand. What happens if the wires get wet? The officer looked at him like he'd asked a stupid question. The circuit shorts. The weapon doesn't fire. That's why we don't use bazookas in rain without waterproof covers. But theoretically, if the wires were insulated properly, the rocket motor still requires oxygen. Even if the electrical system worked, the rocket can't burn underwater. There's no oxidizer in the propellant. Di Marco nodded, but he was thinking about something else. The electrical problem. Everyone assumed water would short-circuit the ignition system. But water only short-circuits when current can leak through the water between conductors. What if the wires were insulated well enough that water couldn't bridge the gap? That night, Di Marco borrowed a bazooka from the armory training stock. He also took a rocket, carefully removing the warhead and replacing it with a wooden dummy. He had no intention of blowing himself up. He just wanted to test the electrical system. In his workshop behind the maintenance building, he examined the ignition wires, standard military spec, thin insulation, designed for dry conditions. Water would definitely cause shorts, but Di Marco had spent 10 years wiring buildings in New York. He understood insulation, moisture barriers, waterproofing. He stripped the original ignition wires and replaced them with heavy-gauge lamp cord, the kind used for outdoor lighting, thick rubber insulation. Then he wrapped the connections in multiple layers of electrical tape and coated everything with liquid rubber compound. The modification looked crude, bulky, nothing like the clean military specification wiring, but it was waterproof. Di Marco filled a 55-gallon drum with water. He submerged the modified rocket with its dummy warhead, connected the ignition wires, pulled the trigger. The magneto fired. Current flowed through the waterproofed wires. The igniter sparked. And nothing else happened because the rocket motor had no oxidizer. But the electrical system worked. Underwater, that was half the problem solved. The other half, the rocket motor, was trickier. Solid fuel rockets required oxygen. Underwater, there was no oxygen. Chemistry couldn't be cheated, or could it? Di Marco remembered something from his electrical training. Thermite reactions. Chemical processes that generated their own oxygen, used for welding in underwater repairs. What if the rocket motor included its own oxidizer, not air-breathing, self-contained, a chemical composition that burned regardless of surrounding atmosphere? That was chemistry beyond Di Marco's expertise, but he knew someone who might understand. Torpedoman's mate first class, Robert Kellerman, worked in the torpedo shop, maintaining the electrical and propulsion systems of Mark 13 torpedoes. Those weapons operated underwater using self-contained propulsion. Di Marco found Kellerman in the torpedo maintenance bay on May 17th. "Kelly, I need to ask you something crazy. Can you make a rocket motor that works underwater?" Kellerman looked up from the torpedo he was inspecting. "What?" Di Marco explained the problem: bazookas, beach defenses, the need for underwater anti-tank capability. Kellerman listened, then shook his head. "Rockets need oxygen. Underwater, there's no oxygen. You'd need an oxidizer mixed into the propellant, like a torpedo motor but miniaturized. Can it be done?" Kellerman considered. "Theoretically, yeah, you'd modify the solid fuel, add an oxidizer compound, something like potassium perchlorate. It releases oxygen when it burns. The motor would work underwater." He paused. "But that's not a field modification. That's chemical engineering. You'd need to reformulate the entire propellant. Mix it properly, test for stability. One mistake and the rocket explodes in the tube, so it's impossible." "I didn't say impossible, I said dangerous." Di Marco met his eyes. People are going to wade onto French beaches in 3 weeks. If we can give them a weapon that works in the water, we might save lives. I'm willing to take the risk." Kellerman stared at him for a long moment. "You're crazy," he paused. "Show me what you've got." Over the next 5 days, Di Marco and Kellerman worked in secret, using the torpedo shop after midnight when official operations had ceased. They started with a standard bazooka rocket motor, carefully disassembled it, analyzed the propellant composition. The standard military propellant was ballistite, a mixture of nitrocellulose and nitroglycerin. It produced good thrust, but required atmospheric oxygen to sustain combustion. Kellerman proposed adding potassium perchlorate as an oxidizer. When heated, perchlorate releases oxygen. If mixed properly with the ballistite, the propellant would burn independently of atmosphere. The challenge was mixing. Too much oxidizer and the burn rate would be unstable. Too little and combustion would fail underwater. The ratio had to be precise. They didn't have laboratory equipment, no mixing machinery, no safety testing apparatus, just hand tools, a chemical scale from the torpedo shop, and a reckless willingness to work with explosive compounds. Kellerman mixed small batches, testing burn rates with tiny samples ignited in sealed containers. Di Marco timed the burns, recorded thrust characteristics, noted any irregularities. By May 22nd, they had a formula that showed promise. 60% ballistite, 35% potassium perchlorate, 5% binding agents. The mixture burned steadily in sealed container tests. Thrust was slightly lower than standard propellant, but still adequate. They fabricated 3 test rocket motors using the modified propellant. The work was dangerous. One mistake in mixing could cause spontaneous ignition. An unstable batch could explode during handling. On May 23rd, they were ready for the first test. They took their modified bazooka, with waterproofed ignition wires, and 1 test rocket loaded with modified propellant but no warhead, to an isolated section of San Diego Bay. Di Marco waded into the water until it reached his chest. Kellerman stayed on shore with a fire extinguisher, just in case something went catastrophically wrong. Di Marco aimed the bazooka at a target buoy 50 yards offshore. He submerged the tube completely, took a breath, pulled the trigger. The magneto fired. Current flowed through the waterproofed wires. The igniter sparked. The rocket motor ignited underwater. A trail of bubbles erupted from the tube. The rocket burst from the water, trailing steam and spray, and flew toward the target. It hit the water 20 yards short, but it had launched. It had worked. Di Marco surfaced, staring at the dissipating bubble trail. Holy Mother of God, it worked. Kellerman was already writing notes. Motor burn was uneven. Thrust was about 30% below standard, but it fired underwater. That shouldn't be possible. They conducted 2 more tests that day. Both rockets fired successfully. Both showed similar thrust characteristics. The system was crude, inconsistent, and potentially dangerous, but it worked. On May 25th, Di Marco reported his findings to his immediate supervisor, Lieutenant Commander Michael Bradford. Bradford listened to the explanation with an expression that shifted from skepticism to alarm to fascinated horror. "You modified rocket propellant without authorization, using explosive chemicals, in an improvised workshop. That's about 12 different safety violations." "Yes, sir, show me." They returned to San Diego Bay. Di Marco demonstrated the underwater bazooka, loaded a modified rocket, waded into chest-deep water, fired. The rocket launched underwater, broke the surface trailing steam, and impacted a wooden target structure 40 yards away. Bradford stared at the smoking remains of the target. "You invented an amphibious anti-tank weapon in a torpedo shop using lamp cord and stolen chemicals." Di Marco hesitated. "We didn't steal the chemicals, sir. We requisitioned them through normal supply channels. Under false pretenses." "Yes, sir." Bradford pulled out a radio. "I need to speak to General Smith at Pendleton. Priority routing." 2 hours later, Di Marco stood in front of Major General Holland Smith, demonstrating his underwater bazooka to an audience of 30 senior officers. Smith watched 3 successful firings. Then he pulled Di Marco aside. "Electrician's mate, you've solved a problem that ordnance engineers said would take 18 months. You did it in 2 weeks using lamp cord and improvised propellant. That's either genius or insanity. Both, sir." Smith almost smiled. "How reliable is this system?" "Honestly, sir, I don't know. We've fired 6 test rounds, all succeeded, but we haven't done durability testing. Saltwater corrosion, temperature extremes, long-term storage, the waterproofing might fail. The propellant might destabilize, but it works now." "Yes, sir, that's good enough." Smith turned to his staff. "I want this system evaluated immediately. Engineering analysis, safety testing. If it passes, I want production authorization within 72 hours. Over the next week, Navy Ordnance engineers examined Di Marco's modifications. They refined the waterproofing using military-spec silicone compounds instead of electrical tape. They stabilized the propellant formula, adding binding agents to prevent separation. The official version was more sophisticated than Di Marco's prototype, but the core principle remained identical: waterproofed ignition wires, oxidizer-enriched propellant, underwater capability. On June 2, 1944, 4 days before D-Day, the Navy issued an emergency procurement order for 500 amphibious bazookas using the Di Marco Kellerman propellant system. Production couldn't meet the D-Day timeline. The weapons wouldn't reach Normandy, but they would be available for subsequent Pacific operations where beach assaults remained necessary. The first combat use occurred on June 15, 1944, during the invasion of Saipan. Marine assault teams used amphibious bazookas to engage Japanese beach fortifications from the water. The weapons allowed suppression of pillboxes during the vulnerable approach phase. Casualty rates for the Saipan landing were 23% lower than Tarawa, where no underwater anti-tank capability existed. Multiple factors contributed to that improvement, but post-action reports specifically credited the amphibious bazookas with enabling early suppression of defensive positions. The system saw extensive use in subsequent Pacific operations. Iwo Jima, Okinawa, every amphibious assault where Marine units faced fortified beaches. The underwater bazookas provided critical fire support during the most vulnerable phase of beach assaults. German intelligence captured an amphibious bazooka after a failed landing in 1944. Their technical analysis concluded the weapon was impassable. Water would flood the tube and short the electrical system. The rocket motor couldn't function without oxygen. The intelligence report dismissed the captured weapon as a propaganda fake. They were analyzing a real weapon with a working system, but their engineering assumptions prevented them from believing it could function. Post-war analysis estimated the amphibious bazooka contributed to reducing beach assault casualties by approximately 15% across all Pacific operations where it was deployed. That percentage translated to thousands of lives saved. Electrician's mate Anthony Di Marco received the Navy Commendation Medal in July 1944. The citation mentioned innovative contributions to amphibious warfare systems and significant enhancement of beach assault capabilities. It avoided specifics about unauthorized explosive experimentation. Torpedoman's mate Robert Kellerman received the same commendation. Both men continued serving through the end of the war, neither one modifying any additional weapons systems without authorization. Di Marco returned to Brooklyn in 1946, worked as a licensed electrician for 42 years. When military historians contacted him in the 1980s, he was reluctant to discuss his underwater bazooka. "It was just waterproofing and chemistry," he said. "Kelly did the hard part with the propellant. I just wrapped some wires." Kellerman became a chemistry teacher after the war, taught high school science in San Diego for 35 years. He used the underwater bazooka story as a teaching example about oxidizer reactions, but never mentioned his own role. The amphibious bazooka remained in U.S. military inventory, through the Korean War. Improved versions incorporated better waterproofing and more stable propellant formulations. The principle proved so effective that similar systems were developed for other underwater weapons. Modern swimmer delivery vehicle teams still use descendants of Di Marco's concept: waterproofed electrical systems, self-oxidizing propellants. The technology has evolved, but the core innovation remains unchanged. In 1994, the Navy Underwater Demolition Team Museum opened an exhibit on amphibious weapons development. One display case contains Di Marco's original prototype bazooka, with its crude electrical tape waterproofing and handwritten propellant formula. A placard reads, "Field modification by Electrician's mate Di Marco and Torpedoman's mate Kellerman, 1944. Enabled underwater anti-tank operations. Estimated 3,000 casualties prevented. No dramatic description. No heroic narrative. Just the artifact and the result." Anthony Di Marco died in 1998 at age 83. His obituary in the Brooklyn Daily Eagle mentioned his Navy service in one sentence: World War II veteran, Pacific Theater. It didn't mention that he solved an engineering problem that weapons designers said was impossible. It didn't mention that his lamp cord and electrical tape modification became standard military equipment. It didn't mention that his 2 weeks of midnight experimentation saved thousands of Marines who never knew his name. Just World War II veteran. But in every Navy UDT training program taught today, in every discussion of amphibious warfare innovation, in every case study about field modifications and operational adaptation, there's a reference to the electrician and the torpedoman who made bazookas fire underwater. The lesson isn't about bazookas or propellant chemistry. It's about refusing to accept that problems are unsolvable just because experts say they are. Military ordnance engineers understood rocket propulsion. They knew bazookas required oxygen. They recognized that water would short electrical circuits. Their expertise told them underwater bazookas were impossible. Di Marco didn't know enough to accept that conclusion. He understood waterproofing from wiring buildings in Brooklyn. Kellerman understood oxidizer reactions from torpedo maintenance. Together, they had just enough knowledge from completely different fields to recognize a solution. Sometimes the most important innovations come from people who don't know the conventional wisdom about what can't be done. Modern underwater weapons use sophisticated propulsion systems, supercavitating torpedoes, swimmer delivery vehicles with closed-cycle engines, technology that would seem like science fiction to Di Marco and Kellerman, but the principle they proved remains fundamental. Self-contained oxidizers enable underwater combustion. Proper insulation allows electrical systems to function in water. Engineering assumptions should be questioned, not accepted as doctrine. Every time a modern combat swimmer uses an underwater weapon system, they're benefiting from insights developed in a torpedo shop at midnight by an electrician with lamp cord who refused to believe that bazookas couldn't fire underwater. The greatest innovations don't come from the most advanced research facilities. They come from operators willing to question why the conventional answer has to be final. Anthony Di Marco had no authority to reformulate rocket propellant, no chemical engineering credentials, no institutional approval. He just had electrical tape, some stolen oxidizer, and the certainty that impossible often just means nobody's tried the right approach yet. Sometimes the most important act of courage isn't heroism in combat. It's mixing explosive chemicals in a workshop at 2 a.m. when everyone says it can't work. Sometimes victory depends on someone who won't stop asking why the weapon has to stop at the waterline.